Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and neurosymbolic AI. This podcast is brought to you by AGI Research Lab and DIA. I'm your host, Brian Landers, and today I am very, very excited to have on our most requested guest. This is just kind of amazing because previous guests that we've had on the podcast have said they've gotten into the field because of the work of our guest today. We're going to actually dive in, probably just do a bit of a reflection on his very influential paper, DreamCoder, and then we'll dive into all kinds of topics like world models, building an academic research lab, exploring the role of program synthesis in AI today. So without further ado, welcome to the show. Would you please introduce yourself?
All right. Thank you, Brian. I'm really happy to be here. I'm Kevin Ellis. I'm an assistant professor at Cornell. I work in AI, program synthesis. I got into this stuff kind of coming out of cognitive science. So a lot of my work and my interests are really grounded in how people think. But I really wear an AI hat most of the time.
Very cool. All right. You are... the topics that you work on in your research are just absolutely what we like to focus on in the podcast. And so, as I said, just, you've been requested in the YouTube comments and anecdotally just kind of, folks speaking with me about the show. So I'm just really excited that we got time to chat. And happy spring break, by the way. I think it's spring break over there at Cornell, right?
Spring break. Yeah.
It's got to be well earned. Someone early on, asked us if we kind of define some key terms before we dive in deep on these topics. And I think it's worth kind of just getting a bit of a rapid fire round where I get your take on some terms that we're going to talk about. First would just be program synthesis. As you mentioned, it's big part of your work, and it's the topic of the show. Can you describe, how do you sort of think of program synthesis?
Yeah. So first, the way that I think of it, I think the way the field has thought about it is changed over time. So like a really long time ago, program synthesis meant coming up with programs in some kind of programming language, given a really precise specification of what program you wanted. The idea is like you write down almost like a math problem, or like what you might see on an algorithms exam. And then what you want to get out is like some code in like Lisp or Python or whatever that like computes the right math function or like does the right thing on the graph. And this, made really strong commitments about what a program is. It said like, it's in the formal languages that humans use to write software. And it also made really strong commitments about how you tell the synthesizer what you want. Like you have to write down basically like some math specifications. I think as time has gone on, it's become clearer that what it means to specify a program can be more loose. You can give examples of what you want the program to do. It also might not be a human that's giving examples of what the code should do. Like if you're trying to write a program that describes how something in the world works, then maybe the kind of stuff you're giving to the system is like data. So maybe it's more like you're learning the program from data. And especially as language models are much more powerful at writing code, it's become clear that we don't have to stick to like the stilted kinds of programs you might write to solve like an algorithms assignment. Instead, we can just write like whatever you would write in Python. And so that opens the door to a whole bunch of just literally anything you could do on a computer. And so now I think program synthesis is much more broader. I personally think of a program as being broader than just like the programming languages that we use, but just something which has both a syntax and a semantics. And it's important that the syntax be recursive and compositional. Like I can kind of build bigger programs out of little ones. And it's also important that the programs, they aren't just like text you write down. You can have some way of executing them. They're like tethered to the real world. And when you have this view of what a program is, it becomes clear that like natural language is a kind of program because we now have ways of executing natural language. So one shift for me and also for a lot of other researchers has been to view natural language as a kind of programming language, which just happens to be a lot flakier than like the
Yes.
kinds of languages we've had before.
Yeah.
So program synthesis, both my view of it and also the field's view of it has changed over time. And right now I think it's very broad, but what's really important is that the program is a symbolic artifact. It's got these pieces that you can recombine. Typically, you can understand what the pieces mean. And it's not just the pieces, it's also the semantics. So you can like execute it. Now, this definition is a little bit, it's a little bit so broad that you could say that anything is a program. And so when people use this term in practice and when I use it, I do mean it in a little bit of like a common sense way. Like I think the weights of a neural network are not a program, even though they can be executed. And even though there is a kind of composition, I can like add more weights for another layer, but I just wouldn't call that a program. So there is a part of this which is kind of informal. Like you sort of know a program when you see it.
That sounds great. Thank you for the nuanced answer there. You mentioned kind of coming from a cognitive science background, and you mentioned, neural nets there. So, that's the symbolic side. What about neurosymbolic? People are very excited about approaches kind of combining deep learning and program synthesis or other symbolic methods. This is clearly a kind of big part of your work and even DreamCoder, what we're going to talk a little bit about today. Can you kind of define for us, how do you see neurosymbolic AI?
Yeah, so neurosymbolic AI just needs to have non-trivial neural and symbolic components which are working together. One, maybe the symbolic thing calls the neural thing, maybe the neural thing calls the symbolic thing. From that perspective, there's a lot of very successful AI systems like AlphaGo or Claude Code, which are neurosymbolic systems. I think that the term is often not applied to those systems, but I think the reason for that is more historical. Like they didn't grow out of communities that liked using the term neurosymbolic, and so they don't often call themselves neurosymbolic, but it's clear that they're very successful. So the general paradigm is working very well.
That's cool. I hadn't heard of Claude Code being considered that, but that makes sense. Yeah, and they're definitely sort of LLMs at their core. There's some systems that are symbolic at their core, and they kind of layer on the neural, maybe for like search guidance, for instance. And then another kind of very exciting thing that I know you've been working on in your lab, and we had your student Top Hiryalko on the podcast, is world models. How do you define world models? I know that's not a it's not trying to be a hardball here. I know, coming from cognitive science, people probably have lots of opinions, but just in kind of, the most general terms, how do you describe a world model?
Yeah, so a world model is an object that allows you to answer questions about the world or questions about parts of the world. And so I think that the hard part here is like defining what the world is, and typically world models don't model the whole world. They model like a video game, or they model like a mechanical part or something. So it's not really the whole world. They like choose some slice of it. But what's important about these systems that they're modeling is that there's some time varying state. And usually also we introduce a notion of actions, meaning that there are variables that we can intervene on. And those variables also have a time component. We can talk about our actions of a time. And what's important to make them really actions is that your interventions only get to condition on things that happened earlier. This is a broader definition of a world model than just predicting the next frame. So often when people talk about video world models or things like Genie, they're predicting the next frame, fully simulating the world. And simulators are kind of the canonical example of a world model. And the kind of stuff that Top and other collaborators and students and people at other labs have been working on, they're a slightly different kind of world model typically, where the goal is not to predict the next frame, but the goal is still to be able to answer a variety of different questions about the world, like what will happen either immediately in the future or far in the future, what might have happened in the past, how do I achieve certain goals? You could ask questions about kind of hidden states about the world, like I might throw a ball behind a screen and I might ask, at what time was the ball halfway behind the screen? So this is a question about the world, which did not make reference to any pixel you could observe. The whole point is that you can't observe the ball behind the screen, but it's a well-formed question. People could answer it. And in order to answer it, we're clearly using our general knowledge about how the world works. So the way that I think about world models is that it should serve a variety of different downstream queries, some of which are not clearly reducible to predicting a simulation of the world frame by frame.
Totally makes sense. We're going to get more into world models later in our conversation today. But thank you for that kind of overview, and it's pretty exciting. And when you think about applications like robotics and things like that, this seems like a critical piece of the puzzle that's been missing. Before we go deeper into DreamCoder, just kind of reflecting on the paper, how did you get into this symbolic work? It's been kind of a pillar of your research. You studied at MIT, and that's where the DreamCoder, the paper came from. How did you discover it at first, and why didn't you get pulled into the sort of deep learning side of things more, or get on the LLM train when it came?
Yeah. So I mean, the kind of dumb answer to that is that I'm old enough that deep learning didn't work when I started doing AI. So I'd be lying if that wasn't part of the reason why I didn't jump on the neural net train immediately. But the real answer is that I was studying AI as a student and encountering all sorts of AI systems that had knowledge representations that were really well fit to a particular domain of expertise. Like maybe you would pose some kind of common sense reasoning problem, you would write down some kind of symbolic model with probabilities, and you would show that like this model was good at answering questions about this common sense reasoning situation. This seems really exciting, and there were all these examples of this, like working in like robot planning or working in like visual perception, where people write down a model and it's symbolic and it really nails like a little narrow slice of a thing that people are good at thinking about and which we think AI should be good at thinking about. But it raised the question of like, where does this end? Like, do we just hand code a bunch of symbolic models that in a kind of piecemeal patchy way, like cover all of intelligence? And that seemed to like miss the point, because the point of intelligence was that no one's programming the stuff into us. We're creating it on the fly. And that seemed to suggest that we should make AI systems that are kind of programming themselves on the fly and assembling these patches of knowledge as needed. And we have great programming languages that we can use to express this stuff. So that meant that AI just needed to write its own programs. And at this time, I was also taking classes from Josh Tannenbaum, and I was learning about like Bayesian AI, and was taking a theory of computation class that talked about Kolmogorov complexity. So it was just like various ideas that suggested I go in this way. So I then talked to Josh about this stuff, and he was like, "Yeah, like I agree. My lab agrees. Like we're working on program synthesis. Join us." And so that's how I got into it.
That is super cool. I just shout out to Josh Tenenbaum. He's an advisor to India. Just amazing thinker. This sort of minds and machines world. This sort of neurosymbolic kind of bridge. Just really always enjoy working with him. What was it like kind of studying under Josh and in that lab? It just feels like a really exciting place to be. And it seems like you all got up to some amazing work. Was it a fun place to be?
Yeah, Josh is fantastic. He gives you a lot of freedom, but also gives you like very good guidance. And his lab is huge and just chock full of smart, interesting people. It's great that he's been able to like lead all this research and like build this team. And I think him and Armando are very special things that MIT has.
This is Armando Solar Lazama, yeah?
Yeah, yeah. So Armando was my co-advisor. He has been doing program synthesis since the early days, and comes at it from more of a computer science as opposed to cognitive science angle. So I chose to be advised by both of them, and it was a really great experience.
All right. Will you help me get Armando on the podcast? I think he has to be
I'll try.
represented
Yeah.
here. Okay.
Yeah, yeah.
He's sort of like one of the, like preeminent people in the field that I think, he's on so many important papers. So I'd love to chat with him. What a legendary, crew to kind of come from in this space. So very impressive. And you've just done amazing things. Let's talk about DreamCoder. So we're actually just a few months shy of the 5th year anniversary of the paper. So congrats for, having it be still relevant to this day, and again, inspiring people to get into the field. That must feel pretty good, yeah?
It's been a while. I don't know, 5 years.
It's amazing how time flies. But it's been quite the 5 years too in AI. If you look at, sort of how
I know we put it out like kind of right before LLMs. AI has been like completely changed in the past 5 years. Yeah.
I mean, even just, every month that you mentioned Claude Code, I mean, it's just like a wild, the whole, every industry is kind of, reeling from all these changes. Just take me back to the origins of DreamCoder. What inspired the original idea?
So what inspired the original idea? Well, so actually, there's several ideas, but in terms of the kind of history of it, when I landed in Josh's lab, he paired me up with one of his PhD students, Eyal Decter, or maybe Eyal Decter kind of fished me out of the class after something. Anyways, I got connected with Eyal Decter through Josh, and Eyal was working on program synthesis. He had this really cool idea of learning libraries. He was thinking about like how children learn concepts, and it just seems like if the concepts were programs and the programs are really big, how would you ever like stumble across those programs? It's a nasty search space. But kids are learning lots of programs. They're learning new things every day, and it's cumulative. They're learning tomorrow builds what they learned today. So the most straightforward, or actually it wasn't that straightforward, but one thing you could think to do that Eyal thought to do is to recycle pieces of programs you learned before when writing new pieces of code. And this suggests learning a library that you carry forward through, if you're a human, during your lifetime, if you're an AI, then during your training run, and using that library to write code. So DreamCoder kind of grew out of the early library learning effort. And it was trying to make it so that it can scale to harder problems, so that it draws more on ideas about human cognition, so that it can leverage what's happening in the deep learning space. And the way that all fit together was with this wake-sleep algorithm. So here is how like the wake-sleep thing happened. So Eyal had done his library learning system, and around that same time, a paper came out called DeepCoder, which was about training neural nets to help search for programs. And these neural networks were trained on synthetic data. So one big issue is that even when you're learning a library, search remains hard. The neural networks are going to be important here. But as you learn your library, that can be used to make synthetic data, because your library gives you good building blocks, and therefore random assemblies of good building blocks make programs that do more realistic things. So this naturally tied into wake sleep, which is an algorithm where you kind of learn to make synthetic data and get better at doing it over time. And that became kind of the general framing of how to combine neural networks with library learning.
Okay, so this wake sleep thing, I think this is a big part of why people are just fascinated with the paper. How much did your cognitive science background influence that? Because it's a very human kind of view of like sort of cognitive processes. Was that at all a part of it? It must have been, because just even the terms of wake sleep, it's not.
The basic motivation is like every smart animal that we know of spends a huge chunk of its time hallucinating vividly. And this is really weird. It's clearly like for something useful computationally, otherwise you wouldn't do it. And so then you have this kind of puzzle of how do you incorporate like a huge amount of computation spent dreaming fake data into your learning algorithm. So it's cognitively inspired in the sense that it draws on this basic observation that humans and other smart animals sleep and they dream. But it doesn't draw. It ended up just kind of by accident. Aspects of the algorithm align well with some of the things we know about sleep, but it wasn't really designed from the beginning to look a lot like sleep. It just was a kind of convergent evolution. So one aspect of the kind of convergent evolution is that during the sleep phase, when we're trained the neural net, we found it useful to both train the neural network on replays of actual data, as well as fantasies or totally made up fake data. And indeed, in the actual brain, you see like replays of waking experience. You also see like totally from scratch generation of fake experience. But we didn't actually do that because we knew that the brain does that. We did it because we were playing with the code and saw that they both help.
Wow.
So that's how the wake sleep eventually became like the framing around which we built the algorithm.
That's actually the true story of human intelligence too. Is just someone was watching our code. No, I'm just kidding. There's so much we don't know about the human brain, and I'm glad that it's sort of inspiration, but not some kind of a claim that like this is how the brain works and that's why it works in the code. It's like no, it's a cool idea and it serves a purpose, and here's what we observed in the results. It's a very pragmatic view of things, but it does really like capture people's imagination. I mean, even again, the language you use, like replays and fantasy, they just, I don't know. It's just a really exciting way to talk about it. So huge props for your naming of things.
It's a fun metaphor.
Yeah. I guess, we won't there. You've done talks on YouTube, which I'll link to some in the show notes about, the exact sort of system architecture. Highly recommend people just dive into the paper. It's a really fun read. See what it kind of inspires you, these days with sort of new tools available to you. But, looking back at the sort of results, did anything surprise you about the sort of, the workings of this system looking back, especially now with so much hindsight?
Yes. So maybe one good surprise and one bad surprise. Like one thing where like, oh cool, it like worked way better than we thought it would, and one place where it's just kind of ugly and like we never sorted it out. So I'll start with the ugly one because it builds naturally on this wake sleep stuff. So the wake sleep story in the original wake sleep from like the 80s, early 90s, whatever. It had a nice alignment with how biological sleep works. There's like a waking phase and a sleeping phase. And we tried that with DreamCoder. And we just found from an engineering perspective, I think for reasons that aren't very interesting, what actually works is this like weird kind of thing where you do a waking phase without the neural nets, then a neural net sleep phase, then like a wake phase with the neural nets, and then like a different sleep phase. We update the library. And it's just kind of like a little bit weirdly interleaved, and the different wake and sleep phases are slightly different. And I think that the reasons why this worked better, it actually worked a lot better. I'm not sure they're very interesting. I think it's more an artifact of lambda calculus and our neural net architecture and just all sorts of things that aren't interesting to sort out. But I was surprised that the scheduling of wake and sleep that from an engineering perspective actually works is just weird and hacky. Like it has a weird wake sleep kind of schedule. It's like one of those like Superman like polyphasic sleep schedules or something. It's really weird.
Oh yeah, yeah. People are into those now with their agents. They can't leave the Claude code for too long.
Yeah. So DreamCoder is a very weird like polyphasic sleep schedule. The thing that I thought was really cool to see happen was the functional programming experiments where it was trying to come up with higher order functions. So we gave it maybe around like 20-ish functional programming exercises. Things like reverse a list or like add one to each element of a list. And we didn't give it like map and fold. We just gave it recursion. So at the Y Combinator, but not much else. And from that, very consistently, you would learn map and fold, even though we didn't tell it to learn that. That's nice because those are kind of the most popular higher order functions. You see them all over the place. They're very foundational. There's also another higher order function called unfold. And I can see the look of surprise. It's a weird one. Most people like never use it in their programming. And it turns out that in order to express like kind of any recursive operation on sequences, you need both fold and unfold. If you're not going to have primitive recursion. So fold is like recursively consuming a list. Unfold is recursively building a list. They kind of are like opposites of each other. So unfold is an oddball. It turns out there's a lot of ways of doing it. We do see the unfold emerges, but it's a little harder to get it to emerge. And it's there's several different forms in which it would sometimes like pop up. And I thought that this was a really cool result, which we actually didn't try to. We weren't like, I mean, obviously we were gunning for the system to work. We wanted to learn map, but we weren't gunning for it to be really easy to learn map and fold, and for it to be really like weird when learning unfold. And for there to be different versions of unfold it could learn. But it was cool to see that actually this system, which was never exposed to human written source code, was spontaneously kind of rediscovering the conceptual naturalness of fold and unfold, and the weirdness of unfold. The conceptual naturalness of fold and map, and just the conceptual weirdness of unfold.
Yeah.
So that was a really fun result to see.
That's cool. It's fun to be surprised by results too, isn't it? Just, you never know what's going to happen, but sometimes it just doesn't work, and that's just sort of the outcome.
Yeah. It's a very common outcome. Yeah.
It's not even failure in science. I mean, just finding out what's going to happen. I love hearing about, surprise learnings from the paper. You mentioned lambda calculus there. What are your thoughts on, and actually, before I ask you this, what is your current work like? What kind of representations are you using for program synthesis these days? Are you still using that same kind of substrate?
Oh, we use Python for like everything.
Yep.
Like it is just empirically the case that large language models are great at writing it. It's great at solving just so many different kinds of AI problems. And if you want to build a practical working system, Python is a great choice. So that's what we actually use today, because the neural networks have gotten so good at writing Python code.
Yep. Totally makes sense. Do you have any thoughts on, we've had Andrew Cropper, who I know you're familiar with, on sort of logic programming or inductive logic programming, ILP?
Yeah. So I love inductive logic programming. Actually, way back when I was first getting interested in program synthesis, I became obsessed with reading Stephen Muggleton's papers. I ended up not going down that route in my own research because I was mostly interested in programs that could serve as simulators, believing that this was close to a world model, and that what I really wanted to capture was like knowledge about the world. But there's lots of kinds of knowledge that don't look like simulators. And also, there's a nice correspondence between the syntax of logic programs and its semantics in terms of like what inferences you draw and so on. And that's just led to a whole bunch of like cool algorithms for doing inductive logic programming. So like PROGOL and like its kind of inverse deduction rules. I might be misremembering because I'm not an expert in ILP. I think it was PROGOL that like have the operators that would do that. But there's a lot of like cool stuff that you can do, which works well in inductive logic programming that just doesn't work very well in like lambda calculus.
Yep, makes sense. Cool. What about probabilistic programs? It seemed like you were kind of big on that in the past. What do you see as advantages that come from probabilistic programs that can't be achieved without them?
If we want our programs to describe knowledge about the world, then our programs need to be able to describe the statistics of the world, and the world is uncertain. If we want a program that predicts what happens when we like turn on our car, like that program should not predict that like the car is always going to turn on. Like it should predict that there's uncertainty and like the car might be broken. Or if I want a program that's going to predict what my cat is going to do when I do something, like obviously that's going to have a lot of uncertainty. And I don't think you can model the world correctly if you just have deterministic rules. And therefore, any deterministic program is going to be inadequate as a world model.
I think that's a good segue into, a topic that you're very excited about, especially in your lab, which is world models. As you sort of explore, how to uncover or build world models, how do you look at that in terms of, sort of symbolic kind of underpinnings, versus this deep learning side? I know that people want to use world models with LLMs, but how do you sort of attack this problem area?
I think that in order to attack it, you need to define what a world model is supposed to be doing. And we have these neural network world models, which take a particular stance on that. Neural network world models like Genie are trying to predict like future frames conditioned on past frames and past actions. So they're doing it like a frame by frame, like perfect simulator. And that's not quite true for things like JEPA, but I think they're conceptually pretty similar in the sense that they view the goal as simulation, either in pixel space or in latent space. Where I think that there's new opportunities for research is when we expand the set of questions that we might ask of our world model, because frame by frame simulation is not necessarily the best way of answering those questions. So, for example, if I'm leaving for vacation and I forget to arrange for my goldfish to be fed, I shouldn't, it's sad, right? But I shouldn't need to, well, no, part of the story is that I remember as I'm leaving. So
That's true.
I remember, and I shouldn't need to simulate frame by frame for the next week to know that the goldfish is not going to have a good time. I should be able to make an inference about the goldfish's state 1 week into the future without committing either to the intermediate time steps and also without committing to the intermediate pixels.
Totally.
So the kind of, so it's a kind of thinking which is abstract both with regards to the state of the world and also abstract with regards to like time. And that you can probably, I don't want to say you can't capture it with neural nets, but I think a kind of black box neural net simulator would really struggle with these kinds of things. Whereas a symbolic approach, even something like chain of thought, would do much better. So if you expand the scope of things that you're asking of your world model, then I think there's new opportunities for research.
100% agree. Yeah, completely agree with that. Hey, why did you, get interested in world models in the first place? Was it kind of a natural evolution of your work? Was it limitations of current AI? Was it sort of, kind of seems like a missing piece of the puzzle for a lot of applications of AI we hope to have, certainly for AGI, sort of human-like intelligence, if you will. But yeah, what got you hooked on the concept in the first place?
So I mean, I think this goes back to cognitive science, like in thinking about if these neural nets and these programs are supposed to be like modeling something in our head, what are they modeling? And it seems like what they're supposed to be modeling is the stuff we know about how the world works. They might model other things like policies or reflexes, but the thing that I felt symbolic methods would be the best fit for and which I think is in people's heads, was stuff that looks like a world model.
Yeah, 100%. I'm thinking back to Top's PoE world, just how cool it is to, that it plays Atari games, and it started doing something cool where it was like simulating the game, like playing it in its imagination, if you will, which feels very much like a continuation of the cool kind of sci-fi themes you had going in DreamCoder. Are there any papers that you've been kind of excited about lately? Tell me some stuff in the field that you've been checking out or been a part of yourself.
One paper that we did in collaboration mainly with Tom Silver and Yishao Liang is exopredicator. This is our attempt at making world models which are abstract both in time and also abstract in how they model the state of the world. It doesn't, we didn't task it with like the goldfish problem, but we tasked it with similar stuff where you're in an environment and there's a bunch of long range behaviors that you need to forecast in order to achieve different tasks like cooking dinner. So like when you cook dinner, you need to like put stuff on the stove, and you then know that in like 10 minutes it will start boiling, but you don't want to simulate all the frames in those 10 minutes. You want to be able to draw some fast inference. And what exopredicator is doing is it's trying to write little programs that define an abstract feature space. So like, is the water boiling? Is the goldfish alive or dead? And then write little programs that describe how the temporal dynamics are of those things. And so it's a program synthesis system combined with like this temporally extended probabilistic reasoning. One thing that we did as like a first step to try and make these world models that are not predicting the next frame, but predicting non-frame stuff and not the next stuff.
This is cool. It's just really exciting paradigms to be exploring. It feels very relevant for applications of AI. Like I said, sort of robotics, and I can just think of lots of places where this is cool. I know you're an advisor to a really cool nonprofit AI organization called Basis. Everyone should go check out the episode you had with the co-founder Zena on a machine learning street talk. That was super cool with our co-founder Francois Cholet. I think it was maybe a NeurIPS, maybe a couple times ago. But yeah, tell me about your involvement with Basis. What are you excited about there that you're working on?
Yeah. So I collaborate a lot with Basis. I like the people, I like the organization. They do a bunch of different stuff. I'm only involved with like a small slice of it. But the stuff that I'm collaborating with them on is all about making agents that learn world models and then try to reason to solve an open-ended set of queries using those world models. So there's one paper that this collaboration has put out called On a Bench. And I think it really gets at the notion that a world model is not about solving any particular task or answering a particular like kind of query, but instead is something that you quickly learn and which can be used to answer like an open-ended set of queries and questions and used to make decisions and draw inferences. It also has I think a nice relationship to ARC-AGI 3.
That was something I wanted to talk about. Okay, we just launched ARC-AGI 3 publicly last week. Definitely feels relevant to the this world model work that you've been up to. I guess just you've worked with ARC in the past. You've been someone who's done really cool work in this space. Just to ask, what do you think ARC-AGI, certainly versions 1 and 2 measure? Like, do you think they actually measure fluid intelligence? Any thoughts on just the benchmark design in general?
I think it's a fantastic benchmark. It actually like spurred a lot of research on few-shot generalization, which in my view is the part of fluid intelligence that it's most directly measuring. It's also just a perfect benchmark for program synthesis. like much of program synthesis is concerned with looking at some input-output examples of a function, inferring the function, and then proving that you got it right by applying it to some new inputs. And the fact that this is the same as supervised learning means that you can have program synthesis go toe-to-toe with more mainstream machine learning methods. So I think that ARC-AGI 1 and 2 were a really strong test of program synthesis. I think we learned a lot from the benchmark. Like in particular, one thing I found really surprising is that I think to date, conventional program synthesis methods have not actually been what's topping the benchmarks. But this kind of program synthesis in natural language or LLMs calling tools like that has done very well on ARC-AGI 1 and 2.
Neurosymbolic AI for the win.
Exactly. Yeah.
Do you think that, this sort of, reflecting back on DreamCoder, that sort of, approach will have any bearing on ARC-AGI going forward? Or is that a promising place for researchers to dig?
So I think that the general idea of wake sleep is really important for a kind of learning that was not as directly tested in ARC-AGI 1 and 2, but is maybe more directly tested in ARC-AGI 3. So the kind of wake sleep that DreamCoder does is a wake sleep that is not a few shot problem. Like you need more than a couple examples to kind of get started, but it's also not like a big data problem. You don't get like 10,000 examples to learn from. And in ARC-AGI 3, like one thing that I really like about the design is that you progress to these levels. And they kind of add new knowledge incrementally. This, I think, more closely mirrors the kind of cumulative learning that people do, where they're going through life and life is just always presenting them with new causal mechanisms to learn, new variations of stuff that they've seen before, and their knowledge is always being stretched a little bit. And that means that you're in this mode where you're interleaving learning and reasoning, and you need to go back and forth between the two processes. And that is where this kind of wake sleep for programs, I think, makes sense. That the devil's always in the details, and if you think about what that means concretely, it like the most naive version of it is like you learn some stuff from level 1, and then you hallucinate a bunch of fake levels or like fake versions of it, and then you like grind your GPUs for a week, and that's like really, really inefficient.
Yeah.
But I think conceptually, when you have these learning problems where you've got like maybe 10 or 100 kind of levels, like that's where wake sleep starts to make sense in this wake sleep with programs.
Yep, absolutely. I mean, is ARC-AGI 3 something you think you'll dive into in the lab?
Maybe. Right now, the benchmarks that we're just working on like other benchmarks right now, and I don't want to like distract the lab or distract my collaborators by saying like, "Hey, work on ARC-AGI 3
Now
right
go to
now."
this.
Yeah,
absolutely.
So, we have something working on mini-hack actually that I think would transfer really nicely to ARC-AGI 3.
So when the time is right, maybe you'll consider it.
Yeah. But the student is making good progress on mini-hack, so I think that I don't want to tell him to do something totally different.
I get this like shiny new thing syndrome or something with benchmarks. Yeah, that's a very wise thing. Tell me more about the lab. So like, I find it very exciting to think about, architecting a lab, and how do you, decide what the focus is, and how do you go about recruiting researchers? What can you tell us about, your position, running the lab at Cornell?
Yeah, so I have a small lab and I work closely with my students. So it's very like hands-on. I am fairly opinionated about like what research directions I think we should pursue. But sometimes, the students push back on me, and then like we do something different. So, it's I think there's just less organizational stuff that I have to do because I choose to have a smaller group and to be more hands-on. So it actually is not that crazy of a transition from being a grad student.
Very cool. I mean, it does sound like a lot more work, and you've certainly earned your position there. I mean, you've done so much cool work, and I know your students really just respect the heck out of you. So it's a bit of an understatement there, I think, in your achievement in running the lab.
Well, I have really good students.
Yeah.
One of whom is here on the podcast.
Yes, Top is amazing. Go watch that episode if you haven't seen it. I so enjoyed it. It's just so cool to watch, like, like I said, AI playing Atari games. It's really fun. Very related to ARC-AGI 3. So at the lab, are you actively recruiting new students? Like, are you looking for researchers to join? Any kind of call to action that you'd want to share with listeners checking out your work?
Yeah. I mean, the main thing that we're working on is trying to learn these world models that are different and I think complementary to these like neural world models that predict the next frames, which allow you to do abstract reasoning about general properties of the world over long time horizons, and which are maybe symbolic, but not necessarily like in a lambda calculus sense. I think this is going to be super important for any kind of agentic AI system. So whether it's on a robot or whether it's like in your web browser, like it has to understand the world at a level that's not just pixels, and to be able to imagine like not just the next frame. So um, I'm broadly recruiting people to work on that kind of stuff. I do collaborate a lot with Basis, so the people at Basis are not my employees or my students, but like one way of working with me in practice is often to like work with Basis. So to the extent that I'm like plugging and recruiting stuff, I do want to plug both my lab and also them.
All right, folks, you heard it here. Go, just check out the work and see if it aligns with you. Talk to folks who are in Kevin's lab. I think that's a good way to kind of, get involved. But Kevin, thank you so much for your time here. I think you're welcome back anytime. You can jump on the pod. We can have short conversations. Hopefully I'll catch you at, whatever next conference like NeurIPS, that kind of thing. But you're just a superstar guest, and I can't thank you enough for taking time out of your spring break to come and chat with us.
Thank you so much, Brian.
Awesome. All right. Well, we'll see you all next time on Abstract Synthesis.